but as usual, we don't get your video or audio. It's only full black screen editing. Okay, fine. Let's start the class. We have question and answer. Okay.
Get settled.
Site cover we are seeing video and Gautam will give us login notification picture. So login is not that much good.
Right.
So
But it is what it is. Okay, so the question is that for set cover, where you have a universe and a family of sets, and the question is find a subfamily such that union of that the subfamily sets cover the entire universe and cardinality of f prime is as small as possible. This is a more general version of vertex cover, and we saw a log n ratio approximation algorithm. However, for this special case of vertex cover, we saw much better approximation algorithm. So the question is can we do better than log n for set cover? The answer is no. We have a negative result which tells you that unless something happens, some complexity collapse happens, that you cannot get an approximation algorithm better than this. Okay, so just like NP completeness gives you a way of giving a negative result for polynomial time algorithms, there are also negative results for approximation. In fact, this takes us very nicely to the first claim we want to show today, and that is we will actually, okay, so here better approximation algorithm unlikely is what I'm going to say. This unlikely is a loaded word, which means that if there is a better approximation algorithm, some unexpected consequence happens. But what we will show today is unless p equal to np, there exists no alpha approximation algorithm for the TSP problem. Okay, so today's topic is traveling salesperson problem. We're going to look at approximation algorithms for traveling salesperson problem, and to start with I'm going to give a negative result. So what is a TSP problem? Recall that your input, a complete graph, some distance on the edges, some non-negative distances on the edges, and the output we want is Hamiltonian cycle with minimum total distance. Since it's a complete graph, there are lots of Hamiltonian cycles. You can, in factorial Hamiltonian cycles. But among all of them, you want to find the one which has the total minimum distance. That is the traveling salesperson tour problem. And we saw that it is an NP-hard problem. The that you don't expect a polynomial time algorithm. In fact, when we say alpha approx, we mean poly time. What we are going to show is that there is not even a good approximation algorithm possible for this problem. Okay? How would I go about showing this? So let's read the contrapositive of this statement. What is it? If there exists a polytime alpha approximation algorithm for TSP, then P equal to NP, right? Okay. Little more specifically, what does that mean? How would I show P equal to NP? Not necessarily TSP. Some NP complete problem as a polytime algorithm, right? Then P equal to NP, i.e. how would you show this, right? I'll give you a polytime algorithm for some NP. Sorry? TSP itself, maybe, or all I need to show is that some NP complete problem, right? Then some NP complete problem so that's what we are going to show. What does it mean by TSP is NP hard? Let's say, forget about approximation. The TSP problem is NP hard means what? If there is a polytime exact algorithm for TSP, then P equal to NP, right? Then some NP complete problem is NP, right? How would I show that TSP is NP hard? We will take an NP complete problem, reduce to this in polynomial time. Towards what consequence? That if there is a polytime algorithm for this, using this reduction and this algorithm, I can solve that problem in polynomial time. Now we are strengthening this statement to say that not just exact algorithm, even if you have an alpha approximate algorithm for TSP, some NP complete problem I can reduce to this in polynomial time. Which NP complete problem would you want to reduce? Okay, so let's just go back and recall how we showed TSP is NP hard. Which problem did we reduce from? Hamiltonian cycle problem, right? So reduction. So we have a reduction from so what did we do? We are given some G, not necessarily complete graph. And here I am interested in Hamiltonian cycle and I want to reduce to a TSP. So this is a Hamiltonian cycle instance. And I want to reduce to a TSP instance. So what does TSP instance require? It requires a complete graph. And the weights on the edges, and the decision version would also require some k, because I am asking is there a cycle with total distance at most k, right? So this is what we want in polynomial time. We want to take a graph. Well, we have actually did this. I just want to revise this reduction, polynomial time reduction, without worrying about approximation for now. We are just going to talk about how did we show TSP is NP hard. We took the graph, made it complete, added some distances on the edge, came up with some value k, and said that this has a Hamiltonian cycle if and only if there is a Hamiltonian cycle there with total distance at most whatever k is. So, what was the reduction? You want to penalize it, the algorithm. So, the reduction is that we will make it complete on the same graph, right. So, it is complete graph on V, and my distance is for all uv 1 if it was an edge and 2 otherwise, right. So, we wanted to penalize if the edge was not there, you do not want the algorithm to use that edge, and what was the distance k? N, right, and this k was n. So, you take your graph, make it complete, put these edge weights for original edges 1 and others 2, then you ask, does this graph have a Hamiltonian cycle whose total length is at most n? If so, that would be a Hamiltonian cycle in the original graph, and if not, there is no such thing, then there is no Hamiltonian cycle in the original graph, right. So, it is if and only if. If you have a Hamiltonian cycle, take that cycle, and that would give you a cycle with total distance at most n. If you have a cycle with total distance at most n, because it has exactly n edges, the cycle has exactly n edges, so it must use all edges with weight 1 or distance 1, and they must be original edges, right. Good. So, this is on the exact world, where this is how we showed its NP hard. Now, I want to take this reduction and say that even if I have an approximation algorithm for a TSP, I can use that to get an answer to my Hamiltonian cycle question by appropriately choosing my weights, right. So, now let us assume, suppose there exists an alpha approximation algorithm. Even using that, somehow I will be able to detect whether the original graph has a Hamiltonian cycle or not. So, what kind of weight should I put here, so that so think about what should be the weights. So, what did we achieve in the earlier reduction? G has a Hamiltonian cycle if and only if the same the complete graph, let us call it some kn with distances, has a Hamiltonian cycle with distance at most n. This is what we achieved by doing this kind of weights, and so it is enough to, I use an exact algorithm which can answer this question. If there is such an algorithm, I can use that to get this algorithm. Now, so what do you want to put now? Where? Here. So what weights? So I want to manipulate the weights here. Okay, how do I want to manipulate the weight? Is that if there is a Hamiltonian cycle, then if there is no Hamiltonian cycle, then you know that suppose I don't have this. I am going to figure out what it is. Let's put 1 here for every h. So if there is a Hamiltonian cycle, there is a cycle of weight n. Okay, if and only if that part is clear. If there is a Hamiltonian cycle, there is a one of total distance n. If there is one total distance n, there is a Hamiltonian cycle. But I don't have a way of figuring out is there one of total distance n, because I only have an approximation algorithm. Okay, so the approximation algorithm, if there is one of total distance n, it will give me something whose total distance is at most alpha n, right? But I want to say that even at most alpha n means that there is a Hamiltonian cycle. If I manage to put weights in a way that, right, it is not just n, even if the graph here has a Hamiltonian cycle with distance total even alpha n, at most alpha n, that corresponds to the existence of Hamiltonian cycle. If I manage to put weights that way, I can even use an approximation algorithm and detect testing that. So what should I put here? Alpha n plus 1, right? So if I just put here, because somebody has told me there is an alpha approximation algorithm. So alpha is told to me in advance. So I just replace this distance by alpha n plus 1. If I do that, then with this weights, G has a Hamiltonian cycle if and only if this complete graph with this distance measure has a Hamiltonian cycle with total distance most alpha n. Let us try and prove this, right. If G has a Hamiltonian cycle, then that complete graph has a cycle with total distance at most n, hence at most alpha n, because alpha is greater than 1. Right, it is a minimization problem, so alpha is greater than 1. Conversely, if there is a cycle here with total distance at most alpha n, then really it cannot use any of the non-edges of the graph, because any non-edge has weight alpha n plus 1. So, it must use only the edges, and its real weight is actually only n, and that corresponds to a Hamiltonian cycle in the original graph. Okay. So, now what can I do? I want to solve Hamiltonian cycle problem. I will make it complete, give this weight and give it to the approximation algorithm and say, tell me whether there is one of weight at most n, because really weight at most n is what I am interested in. I will ask that. Approximation algorithm will say, well, I can't find one of weight n, but I can give you one of weight alpha n. But really, no, you cannot really. Whatever weight alpha n should be the weight n. We know that, right. So, we are trying to manipulate, we are making the gap between the existence and non-existence so huge that even an approximation algorithm cannot, cheat us between the existence of a Hamiltonian cycle or not. That is all. So, somehow we can make this weight very large, so that if there is a cycle of length 2n here, weight 2n here, then I do not know whether that would correspond to Hamiltonian cycle or not, 3n, 4n. But we ensured that either you have a Hamiltonian cycle of weight n, or it starts with alpha n plus 1 at least, there is nothing in between. So, even an approximation algorithm which can go up to this point will only find a Hamiltonian cycle. Okay. However, when I said, I mean, so this is a negative result about any alpha can actually be even a polynomial bound. But the consequence here is that if there is such an algorithm, P equal to NP, but for set cover it is not that. Okay, there you require a different kind of an argument. I mean, there is no such negative result for set cover. It's not that if there is something better than log n ratio, then P equal to NP. That's not true. We don't have such an evidence, but some other evidence is there. But so this kind of evidence is not very common in the approximation world. Okay, so things are bad with respect to Hamiltonian TSP problem. So what do we do? Right? It not only NP hard, you can't even get a good approximation algorithm. So what we will do is we will actually restrict our instance to the special kind of TSP, which actually come up in practice. Then we will see that there we can do some good approximation algorithms, and that takes us to this. Triangle TSP. Here distances satisfy triangle inequality, that is for all triples x, y, z, distance from x to y is less than or equal to distance from x to z plus. Right. So remember, it's a complete graph, right? So there is an edge between every pair. So this a direct way of going from x to y, that distance is less than or equal to going through some other vertex. Does this distance satisfy triangle inequality? Maybe not, right? So I might have 1 and 1 and alpha n plus 1 here, which means the direct distance is much more than going through some other vertex. So it could happen that in your graph, this edge was there, this edge was there, but this edge was not there, and so you put a weight of alpha n plus 1, and so. Okay, so we're going to look at this special TSP instance and try and design good approximation algorithm. But before that, let's first show that it is actually an NP-hard problem. Right? With the, by making this assumption, are we making the problem too easy that it's actually polynomial time solvable? So the first claim is that the triangle TSP problem is still NP complete. Okay, so what is the problem? You are given again a complete graph with distances on the edges satisfying this inequality and a parameter k, and I ask, is there a Hamiltonian cycle whose total cost is at most k? Right? That's the decision version of the optimization problem. So the fact that it is in NP is clear. What is the witness? A cycle, and I would just verify that it is actually a cycle. It visits every vertex and add the cost and check that it is at most k. Right? So it's an NP. Right? The witness would be a cycle, and verification algorithm would check that it visits all vertices and total distance is at most k. These two are easily polynomial time checkable. Now I want to reduce from again Hamiltonian cycle to this problem. So all we have to do is to come up with costs like the way we did for TSP, but just make sure that it satisfies triangle inequality, right? So poly from a known NP hard problem, which is the Hamiltonian cycle. So the instance has G, V, and you ask, is there a Hamiltonian cycle in the graph at all? And I want to reduce to this TSP instance, so make it complete. Now I have to define my distances to make sure that the distances satisfy triangle inequality, and I can, it's an equivalent instance, right? So we actually did this. So what are the distances? Oh, okay. So 1 and 2. Oh, that's what we did. So the 1 and 2 actually satisfies distance. So d of uv is 1 if uv is in the edge and 2 otherwise. So it's an equivalent instance because G has a Hamiltonian cycle. What is K? K would be N. G has a Hamiltonian cycle, then there is a cycle whose total distance is at most N. If there is one of total distance at most N, it must use, because there are N edges, it must use the original edges. Why does it satisfy triangle inequality? The distances? Well, we have to prove this. For every x, y, z, we have to show that this happens, right? So, right. Yeah. So, if dxy is 1, then we are done because that right hand side can be 1 or 2, or actually even it's at least 2. Right? No, the sum. The sum must be at least 2. Sum must be at least 2. It can be as bad as 4. But it's at least 2, and so I mean this is at least 2. That's all I care about. This sum, right hand side is greater than or equal to 2, and this is at most 2. That's it. Right. So it satisfies triangle inequality, and you have the equivalence, and you have this reduction, which is polynomial time. So all of that together is NP complete. Now let's design some. I'm going to give you a good approximation algorithm for this problem. So recall the approximation algorithm we have seen for vertex cover using matching or using LP. Typically used some polynomially computable bound. For vertex cover, it was maximum matching, was a lower bound for vertex cover, and we somehow used that. Or LP solution was polynomial time computable, we use that to do our comparison. So here also, we want to find minimum weight Hamiltonian cycle on a complete graph with weights on the edges. So the polynomially computable parameter which we are going to relate to is the minimum spanning tree. Okay, this is something we have done very efficiently. You can compute. So, given a weighted graph, I can compute this minimum spanning tree. So that's going to be our comparison. So, okay, let's make this following observation, right? What can you say about weight of minimum spanning tree and weight of minimum weight Hamiltonian cycle? This would be less than or equal to, okay. Why is that? That alone doesn't tell me. So Hamiltonian cycle uses n edges, that uses n minus 1 edge. So take a Hamiltonian cycle, the minimum weight Hamiltonian cycle. Take a minimum weight Hamiltonian cycle in the graph. Right? I remove one edge. This is a spanning tree. It spans every vertex, it's a tree. So if any, the weight of the minimum spanning tree would be even less than this, right? Because it's among all spanning trees, that is the minimum spanning tree. So the minimum weight spanning tree's cost would be less than the weight of this Hamiltonian cycle minus this edge. So in particular, if all edge weights are strictly positive, then it's even strictly less than that. Okay, so to the proof, take the minimum weight Hamiltonian cycle, remove an edge, what we get is a spanning tree. Okay, so this kind of contrast really helps. This is something very easily computable term, whereas that is an NP-hard problem. Okay, so we always relate like we did matching and vertex cover. Okay, this is going to be of use. We'll come back to this. Now here is our approximation algorithm. Find the minimum weight spanning tree. It's a complete graph, every edge is there. So which we can do in almost linear time. Double every edge, to make every vertex of even degree. To get, let's call this new graph T prime. So what did I do? Sorry. So your spanning tree may look like this. Okay, let's call these A, B, C. These are the vertices of the graph, and I applied Prim's algorithm or some algorithm, found minimum weight spanning tree, and I just doubled every edge. And this is my T prime. Okay, and what did I do? I made every vertex now of even degree. So now I'm going to work with this subgraph T prime. T prime is exactly this subgraph, where every edge doubled. Since every vertex is of even degree, there is what is called an Euler tour, Eulerian tour in the graph, which also you can find in linear time. Okay, so find an Eulerian tour in So this algorithm uses, lots of little things you have learnt in the whole course. Minimum weight spanning tree, Eulerian tour. So let's say on this example, how would the Eulerian tour look like? One Eulerian tour would be, I might just start at A. So Eulerian tour, remember, it visits a cycle that visits every edge exactly once. and that exists if and only if every vertex has even degree, and you can just follow through. I mean, blindly start at a vertex, because every vertex has even degree. If you can get there, you should be. There is a way to get out. That's what it requires. So I can go from A to B, C, D, go back to C, B, E, F, G, F, B, H, B, A. That's an Eulerian tour. Okay. Now I am going to pull out a Hamiltonian tour out of this by short circuiting. Remember, my graph is a complete graph. So there is an edge between every pair of them. So let me just say short circuit to get a Hamiltonian cycle C. So what is my C? So I basically keep track of repeated vertices and don't repeat vertices. That's all. So I start from A, go to B, C, D. Instead of going to C again, since C has been already visited, I'll skip that. B has been already visited. So F, I'll go directly to F. So I will start with, I don't have any other color, I think. Okay, so we'll try. So I'll go from A, B, C, D, then skip all this, directly go to F. Then come to E, skip E and F again because they've been visited. So directly go to G. So I go to F, E, G, skip F, B and go directly to H, and skip B and directly go to E. Okay, so that would be my Hamiltonian cycle, and that's my output. Okay. Did some magic, found a minimum spanning tree. The answer sounds like some object which I can find fast. From there I got an Eulerian tour. From there I just generated this short circuiting Hamiltonian cycle. Okay, so output. Okay, this looks like a heuristic. Somehow started from minimum spanning tree and managed to get something out of it. I want to now, what do I want to argue? I want to show that this is a two approximation algorithm. The claim is the weight of C which I finally output is at most 2 times opt. By opt I mean the weight of the minimum weight Hamiltonian cycle, which I don't know, but I have some way of bounding it using this, which we will use. Okay. So let's call this Euler tour as something. Third step, let's call this some C prime, which is the Euler tour. Yeah, you can. That's what it amounts to, but going it this way helps the proof that it's at most 2 times. So what is the weight of C prime, the Euler tour? Let's see. The total cost of this Eulerian cycle, 2 times? Not n minus 1. The edges have the weights. So it's 2 times weight of minimum spanning tree, right? Because what I did is I took the minimum spanning tree edges, double them, and every edge of a minimum spanning tree is visited twice. which is less than or equal to 2 times weight of min weight Hamiltonian cycle by observation. Okay. What is the weight of the Hamiltonian cycle I output? What is the weight of C? This is the weight of C prime, the Eulerian cycle. This Eulerian cycle's total weight is 2 times the weight of minimum spanning tree, which by that observation is bounded above by 2 times the weight of minimum Hamiltonian weight cycle. But what is the weight of this cycle? Yes. So what did we do here? We did short circuiting. So we came, so this was the Eulerian cycle which went like this. From here, instead of going this, I directly use this H. That's what this happened. Instead of doing DC, CB, BF, I went directly DF. And by triangle inequality, this is the place where we use triangle inequality. The cost of DF is less than or equal to DC plus CB plus BF, right? You just have to apply that triple thing twice. And so on and so forth. So every edge I traversed here, the direct edge cost is less than or equal to the cost of going through all these vertices. So my weight of the Hamiltonian cycle is less than or equal to weight of C prime. This is by triangle inequality. And then we know that that is at most 2 times the optimum. Okay, so this was improved, the ratio was improved to 1.5 using the following idea. So, why did we double every edge? To get Eulerian tour. So, what do I need for Eulerian tour? Every vertex should have even degree. So, why double every edge? There are, in my minimum spanning tree, there are some vertices which are already having even degree. Why don't we leave them alone? Okay. Take only those vertices with odd degree. They are even number of them, right? Because in any graph, number of vertices with odd degree is even number of them. There we are going to do something else to give them an extra degree for those odd degree. Just that alone, and we are going to augment it. Okay. So that algorithm works like this. So what do I erase? Okay, so let me just erase this. So what we want to do is the following. Find a minimum weight perfect matching M on the odd degree vertices of T. So let's just go back to this graph. So what do I do? So this graph is A, B, C. So this is my minimum spanning tree. So which vertices should I worry about, or which vertices should I not worry about? C is already of even degree, so don't bother. Two, three. So everything else basically looks like. No, this is of even degree. Good. So don't bother about it. So essentially 1, 2, 3, 4, 5, 6 vertices are the odd degree vertices. So I remove the even degree vertices from the graph. look at the only odd degree vertices and look at the edges between them. Remember, it's a complete graph. So when you induce this subgraph, that's also a complete graph. For this complete graph, I find the minimum weight perfect matching. There are lots of perfect matching because it's a complete graph. Find a minimum weight perfect matching. Okay, we went through this algorithm using some primal dual algorithm, putting some costs and so on. So among all perfect matchings, you want to find which has a total minimum weight. So that matching may do the following. It might map, let's say, A and H. It might map F and G and E and F, let's say. So there are 6 vertices. So this is my matching edge. For example, I mean, I don't know what it will do because it's a minimum weight. So I give this odd degree vertices alone to a subroutine which will find minimum weight perfect matching. So my T prime would be T union M. So this is my T prime. So for example, if it uses one of the existing edges of the T, then I double that. Like here, right? The minimum weight perfect matching at this edge FG, I'm going to add an extra edge. So now this is my graph. This is Eulerian. Why? Because every vertex has got an even degree, because those with odd vertices have exactly one extra degree. Even degree vertices were not touched. Those with odd degree vertices got exactly 1 degree extra. So, this edge is there. What do you mean? It's a complete graph, so every edge is there. No, so what I am saying is, you are matching. What are the vertices I am worrying about? A, H, D, E, F, G, right? This is a complete graph. I give it to my perfect matching algorithm. I say give me minimum weight perfect matching. So that, suppose it did this. This was the matching it produced. Then I add these edges to my spanning tree. It so happened that FG is also a spanning tree edge, so it will get doubled. So my T prime is whatever the original minimum spanning tree is plus this perfect matching. If there is an edge which is also in T and M, then it will appear twice. So in the process now, what have I done? I have made every vertex of even degree. And now it follows step 3, find an Eulerian tour. So I can find that in T prime and short circuit to get a Hamiltonian cycle. How do we argue now that the cost, the claim is 1.5 times odd. Okay, so this requires okay, so let me erase this in. So the claim is weight of the cycle produced is at most okay, so weight of C, the same as before, is less than or equal to weight of C prime, right? This final cycle produced, its weight is less than or equal to weight of C prime because we did short circuiting. We took an Eulerian cycle, we did short circuiting to get there. What is weight of C prime? This is weight of T plus weight of M. Right? T prime is T and M. Weight of T I know is at most minimum weight. Right? This is opt. This is less than or equal to opt plus weight of M. We'll claim that weight of M is at most half times weight of or opt basically. But what is opt? It's the minimum weight Hamiltonian cycles weight. That's what I want to show. Once I show that, I'm done. Right? Earlier this was this opt plus opt, it was 2 times opt, we are done. Now it's not the entire all edges duplicated, but it's just a matching, and this is a minimum weight perfect matching of the odd degree vertices of T, and I claim that that is at most half times opt. So what do I do? Okay, so let O be the minimum weight Hamiltonian cycle. It's actually pretty simple, you know.
If you look at the path between these two vertices in the cycle, so that weight is greater than the infinite which is there.
Okay, so
Each matching at weight is less than.
okay, so first let's do something simple, right? This minimum weight Hamiltonian cycle contains all the vertices of the graph, right? So maybe some of them are odd degree in T, some of them are not. Let's say these are the odd degree vertices in T, right? Because that's what I care about. Matching is all about the odd degree vertices in T. So I again short circuit this to keep only the odd degree vertices in T. Let's remove the even degree vertices in T from this cycle, right? So what I do is I look at only this new cycle in which I only have the odd degree vertices of T. Remove the remaining ones just to make life simpler, and I get a new cycle. Let's call it O prime. That cost is less than or equal to O because of the triangle inequality anyway. And O prime obtained from O only odd degree vertices of T. Okay, now is it easy to see? You can think of O prime as actually 2 matchings, right? It's a cycle on vertices of odd degree vertices. You can think of it as 2 matchings, M1 and M2, right? So O prime can be split, partitioned into 2 matchings M1 and M2. So weight of O prime, which is less than or equal to weight of O because of the short circuiting, is equal to weight of M1 plus weight of M2. Both of them are perfect matchings on the odd degree vertices, right? So both of them are, it's greater than or equal to 2 times weight of M, because this is a minimum weight perfect matching. These are also perfect matchings. So weight of M is less than or equal to weight of M1, weight of M is less than or equal to weight of M2. So weight of what I get? Weight of O is at least 2 times weight of M prime. That's what I get. That's what I wanted to show. So weight of M is at most half times weight of O. This has been the best approximation ratio for a long time. I think we don't know anything better than that. But okay, so the next about 15-20 minutes I will talk about a polynomial time up. So we have seen a variety of approximation algorithms now. That with one with ratio 2 vertex cover, again that's been the best for quite some time. Ratio 1.5, ratio log n, and for general TSP we even have a negative result which says that you can't get better than log n. Sorry, you can't get any constant approximation or any approximation ratio. And here is a problem where you can get arbitrarily close to 1. And that is the subset sum. Okay, so the decision version is your input a set of n integers and a target integer t. Does there exist, okay, let's call this set, a subset S prime of S such that summation x in S prime is equal to 2. Okay, can I get some subset of these integers that add up to exactly t? This is like the knapsack problem, right? I have a knapsack with capacity T and I have a set of objects. Can I fill it up with some subset of objects? So, my S could be then I ask, can I get some subset here that adds up to 36? So there are lots of ways actually. 7, 9, 15, what? 15, 21 add up to, I can add 18, 15, 2, 1. Yeah, so there are many ways you can get this, and so the question is there some subset that adds up to this? One can show that this is an NP-hard problem. You can reduce SAT to it. I think Karman has a reduction which actually reduces from SAT, but this is sort of related to knapsack, partition. There are different kinds of problems related to this. So this is one of those standard NP-hard problems. What is the optimization question? Is to find the largest sum less than or equal to t, right? So the optimization question is the largest number obtainable from your set S, right? It's like this max SAT question asks, is it satisfiable, and max SAT is okay. If it's not satisfiable, give me the maximum number of clauses you can satisfy. Similarly, here saying, if you can't get the target, then give me the maximum you can get by from your set.
After I had 21, then I had 18, got 39. Then I counted 9, counted 7, but then I had 2.
Right, but I may get something even better by skipping 18. It is like knapsack again. So you are trying to be greedy and you say, okay, I will pick 21, I will pick 18, exactly like the greedy choice. So I get 39, suppose the t was 42. You are going to do it in decreasing order. I'll take this, and I cannot add any of this. I can add 2. In this case, it turns out to be, you can actually get exactly 42. But that's sort of a greedy choice. You may not even want to pick 21, and you may be able to get something better. So come up with examples where this greedy does not necessarily give you the optimum. Hey, I mean, I think we did this in the knapsack problem. So for example, so if my S is 15, 18 and 21 and my target is 34, you might pick 21 and then you are stuck, you can't pick anything. On the other hand, if you don't pick 21, you can get this sum and get better, less than or equal to this. Okay, so clearly there is an exponential algorithm. That's not very hard. You can try all possible subsets. Okay, let's first generate an exponential algorithm in a very systematic fashion. Then the goal is to get something approximate. So I'm not going to get this exact number, but I want to get something close to the optimum very fast. In fact, we'll argue that you can get arbitrarily close to 1 plus epsilon ratio we can get. So, an iterative algorithm, let's call it. I don't know really. Is greedy a 2 approximation algorithm? No, I don't know. I'll leave that as a question and for you to check. Look at it in decreasing order and keep taking values into your set as long as you can. Okay, so what we are actually going to give is a so let me mention these two words which keeps coming: polynomial time approximation scheme. It's nice that such algorithms exist, and there is one which is fully polynomial time approximation scheme. What are these problems? These schemes? These are algorithms with approximation ratio 1 plus epsilon. You give me any epsilon, I'll get close to 1 plus epsilon. So, these algorithms take some error parameter and produce a solution. It's a maximization problem, so I will never be able to produce so greater than or equal to 1 by 1 plus epsilon times opt. That is the solution produced, the opt by the solution is less than or equal to 1 plus epsilon. Because opt is a larger number, because it's a maximization problem, I am going to produce something which will be slightly smaller, and the ratio is never more, it is less than or equal to 1 plus epsilon. Right? The opt by solution would be greater than or equal to 1, because opt is it's a maximization problem, but it's arbitrarily close to 1. That's what it's saying. But somewhere you have to pay for it, right? I mean, what do you mean by arbitrarily close to epsilon? Epsilon can be 0 then, right? Where do I pay for it? In the running time, right? So, in the running time, for pitas, would be n to the 1 over epsilon. So, if you want arbitrarily close, you are going to spend more and more time. Fully polynomial time approximation would be polynomial in 1 over epsilon and n. So, 1 over epsilon won't be, there is actually another term called efficient polynomial time approximation scheme, where the running time is some f of 1 over epsilon into n to the over 1. This does not depend on epsilon. So, fully polynomial time epsilon algorithm schemes are very good, which tells you that they are polynomial in n and 1 over epsilon. Of course, there is a dependence on epsilon, but it is So, I'll outline a fully polynomial time approximation scheme for this problem. Okay, I won't get into the complete details, but I'll just give you an outline. So, fully polynomial time okay, first let me give me the exact algorithm in an iterative fashion. What it's going to do is suppose Li is all possible sums from x1 like a dynamic programming I'm going to do. So from x1, x2 up to xi, I look at all possible sums I can get and I've stored it in this list Li. Li is a list of numbers. And how do I get Li plus 1? All possible sums from x1 to xi and xi plus 1. Basically, I'll also keep Li union. So I'm very informally writing here. Li plus x, Li plus xi plus 1. Where yi is in Li. So, let's say I have stored these numbers 3, 15, 18, 21 are all what I can get. This is my Li and my new number, my xi plus 1 comes as 6, let's say. Then I will keep this set plus for each one of them I am going to add 6, right, because I have obtained, this is some subset of Li x1 to xi and I got the sum. So now I add x, so I get 9, 24, sorry 21, 24 and 27 and merge these two, take these two lists and remove duplicates. So this will be removed. So 3, 15, 9, 18, 24, 21, 27 will be this new list Li plus 1. I just keep computing this Li plus Li's and all the way. So my algorithm would be start with L1 for I equal to 2 to n, compute Li from Li minus 1, delete values greater than t because my target is t. Keep doing this. Oh, 6 also to it. This will do it, right? In my original list, I should also have 0. So then 6 will be added. Empty set also is there. Yeah. So this is my algorithm. So finally, pick output the largest from ln, right? This is the exact algorithm, nothing approximate. I computed all possible sums I can obtain from x1 to xn, which are all less than t, and pick the largest guy from ln, and that gives me the answer, right? So now how do I approximate it? So this is again 2 power n algorithm because these li's are all exponential in, it's like 2 power I sizes. So to approximate, what I will do is the following. In Li, so when I compute this Li plus 1, if a lot of numbers are close to each other, I just delete things and say one of them will represent another. So to approximate, so let's say some error epsilon is some error parameter. So I could keep this in sorted order, okay. Sorry, compute Li plus 1, okay, Li from Li minus 1. So this is what I will do, scan Li, after I compute Li, scan Li in increasing order. I don't know whether I should do in decreasing order. And delete so this is my goal, sort of, right? I want to produce not exactly opt, but something which is at least, which is less than opt, but it's at least opt by 1 plus epsilon. So in my list, I have this element which is less than 1 by 1 plus epsilon times this, then I am going to delete this. Which are, yeah, less than 1 by 1 plus epsilon. Epsilon is, so let us call it delta, because this, I do not want to confuse this with my original epsilon, the previous element. So I will remember this element, and then I scan and say if this is less than 1 by 1 plus delta times this, then I am not going to. So this element somehow represents this element, because I am looking for an approximate solution. Because what is my goal? I do not want to spend exponential time, and keeping all these big lists is a problem. So I want to prune this list, prune it in a way that I still do not lose the approximation. So if these two elements are close to each other, I am going to throw this and say this guy will do as good a job here, and I keep doing like this, and that is all I do. Okay, I mean this is just a pruning step. So what do I achieve out of? So now, what delta do I use? I'll come to that. But if I do this, then, so after pruning, number of elements in Li would be, so now the consecutive elements are sufficiently spaced, because the next element is bigger than 1 by 1 plus delta times this, right. So imagine I have, and the maximum element I will have value t, right, because anything less than t I delete. So suppose I have doubled every element, then how many elements will I have? Suppose the consecutive elements are at least 2 times apart, then how many elements will I have if maximum I will have is t? Log t, right, because I would have 1, next element will be at least 2, another will be 2 square, and I am going only up to t. Here I am not doubled, I have done 1 by 1 plus delta times, so it will be log t to the base 1 by 1 plus delta. I mean it achieves this goal of making the size of Li small. So it turns out if I choose my delta to be, so okay, so what is my goal? Somebody has given me an epsilon, algorithms take epsilon and says don't have to solve this problem exactly, I want a number which is less than or equal to t, but it is at least opt times 1 plus epsilon. So epsilon is given to me, so I will use this error parameter to be something like epsilon by 2n. Somehow that seems to work, because these errors are accumulating, right? When I compute Li from Li minus 1, there is a certain error, and then I am going to do the same thing from Li to Li plus 1, and eventually, so the algorithm is simply the same. I am going to do this iteratively and then prune with this error parameter epsilon by 2n. If you keep doing it, then I think, okay, I will just cut the story short and say that so the algorithm makes just a simple modification, that start with L1, compute Li from Li minus 1. Once I compute Li, shorten it, because this was the one which is causing me huge running time. Now the Li's values have become smaller, so log t by this, which turns out to be, if you do some approximation, it will be some order n log t, which is a polynomial function on the input. If you do this simplification, make some approximations for 1 plus this, so it never, your Li's never go beyond n log t. N by epsilon or something. I think that, yeah, probably. So your algorithm running time becomes polynomial in n over epsilon and log t, because you are going to do this n times. And the final solution produced, one can argue that the errors accumulate only so much that if at the end, if you pick the largest from your Ln after even doing this pruning, you will have a representative element. You might have lost the real big I, which is less than or equal to your target, but there is a representative element which will be at least this much. That largest element from your final prune list you will output will be at least this much. So it's fully polynomial time approximation, because the algorithm's running time would be some poly in n and 1 over epsilon and log t, which is my target. Okay, I think I will stop here. This analysis is there in Karman in details. It's just some calculations of this step, that why you have the final solution produces at least this much. And the intuition is that we ensured that the elements are close enough only what we deleted. So if you deleted somebody, there is some representative whose value is at least this much sitting there. Okay, so that's sort of a variety of approximation algorithms. Those that get arbitrarily close to 1 approximation ratio, and log n approximation ratio 2, 1.5, and yeah, okay. So we'll see some more next time.
Just 3